I am the nature hacker, and this is your world. So I want to talk about Nobel metal battery, aka the electroplating battery. And so I think I want to go this route of calling it the electroplating battery because that's really what sets it apart. Is that instead of having an anode and cathode that kind of change composition during charge and discharge, this battery will actually electroplate pure metal as it charges, and then it dissolves that metal in discharge. So this is the only battery out there that does this. So this is an electroplating battery, so I kind of want to term it that now. So for germanium has an electrode potential of around 0.2. So that's good because if iridium has a potential, if the highest metal has a potential of 1.8, and you have 0.2 as your low potential metal, your anode, and you have the high one, 1.8, as your cathode, then the difference between those two is the voltage of your cell. So before I was using copper, which is around 0.6. So 1.8 minus 0.6 is about 1.2 volts, which is what I was getting. But germanium is the lowest positive metal, so we could use it and squeak out 1.6 volts potentially. The only problem is that the thing with the highest potential is the thing that is going to get reduced. Okay, so when we charge up the germanium iridium battery, the germanium only has a potential of 0.2 for it to be reduced into the metal form to redeposit on the anode during charging. Now the problem is that water is around 0.4 or so, and so we're using an aqueous HCl electrolyte. So that means that the water is going to get reduced first and basically electrolyzed or whatever. So we want to make that water so it's not going to get reduced, so that the germanium metal gets reduced instead, so it actually charges the battery instead of creating oxygen and hydrogen gas or whatever. So how do we get water's potential to go lower than 0.2? Well, the easiest way is to degas it, because oxygen is what brings water's, dissolved oxygen is what brings water's potential up and makes it so we can't recharge the battery. So if we degas it, if we hook it up to a vacuum and suck out all of the air from the water, then it goes down to 0.2, so we're right on the cusp. But if we add hydrogen in, like a reducing gas hydrogen, then the potential of water goes down to like negative 0.6. So it's just totally out of the equation if we add some hydrogen. So as we know from before, we need oxygen gas in the electrolyte to be able to give us good amperage. Now, so what we're going to need on our batteries, we're going to need an oxygen tank for discharging. For using the battery, we're going to need an oxygen tank. So we might just pressurize oxygen into the battery, or we might bubble oxygen through the battery. I'm not sure yet. I'm going to test different possibilities. But then once we're done discharging it, we're going to want to degas it, so have a vacuum suck all of that dissolved oxygen out, and then we're going to have something inject hydrogen, either just pressurize with hydrogen or bubble hydrogen through as we charge it. So that's how we're able to charge the germanium battery. So, for the benefit of about 0.4 volts, we have to have a hydrogen tank, and we have to have degassing going on. With the copper iridium battery, or whatever the cathode needs to be, it doesn't have to be iridium. With copper, we don't really have to worry about it because it's at around 0.6, and even water with dissolved oxygen in it is around 0.6, so we might be able to get away without even degassing it. So copper is a little easier, but if we want to get that extra 0.4 volts from the germanium, we're going to need to degas the electrolyte and inject hydrogen in order to recharge it properly. So we might be able to get about 1.6 volts. We just need a hydrogen tank and an oxygen tank. And this kind of dovetails nicely in with, alternative energy. Lots of people are doing electrolysis. So if they're doing electrolysis, that means that they can create hydrogen and oxygen, and then us battery people can buy the hydrogen and oxygen from them and use that in our battery system. So, I think it all dovetails in nicely, with the new economy that will emerge in the new society. So, yeah, I'm pretty excited about it. 1.6 volts, I think that's pretty decent. Another benefit is that this battery will never go bad. The electroplating battery will always work. And even if something goes horribly wrong and, I don't know, you put in a crap electrolyte and it's jacking stuff up, you can always recover the metals out of it, because the metals are pure metals. It's not like lithium iron phosphate or some crazy combination like that. It's just pure metals, so you can always just do traditional, electrolysis to get things back to normal and stuff. So the battery will never go bad, and you might just have to maintain it once in a while, like you might have to replace the hydrochloric acid once every couple years, or that's really all you would ever need to do. So yeah, that's pretty much it. So yeah, that's the electroplating battery, and we're going to try to use germanium. And it is possible to use metals with negative potentials, but one, you're not going to be able to use water, because like I said, water will preferentially reduce. Like a negative metal like magnesium, lithium, aluminum, you're not going to be able to use water. So you're going to need to use an organic solvent, like I think it's diethyl carbamate is what they use. So you're going to have to dissolve salts in diethyl carbamate, and yeah, that's pretty much it. And you're going to have to use basically like fluoride salts. You're going to have to like dissolve sodium fluoride and diethyl carbamate. It's just, I don't know. First of all, I don't think you'd be able to get as much amps out of it, because you can't use an acid, because acids will discharge it. Because acids have a higher potential. So yeah, it's more tricky and difficult to do that. So yeah, you could use negative metals and use them in an electroplating battery. It's just more difficult. And then the anode, you're going to have to apply such a high voltage that the cathode might get jacked up over time. If you're using an iridium cathode in the germanium battery, the cathode will never get messed up. But if you're using like magnesium or aluminum, the potential is so big, the voltage potential is so big that during discharging you might oxidize the cathode over thousands of cycles or whatever. So it'll still be better than a normal battery, but your iridium cathode will jack up over time. So anyway, just more updates on the Nobel metals / electroplating battery. So thanks for watching. I am the Nature Hacker. Do work.